Hello. Some of you had some problems with half-life problems, and so I wanted to go through a couple of them just to kind of actually make sure that you get some more experience with half-life problems and look at how they are set up depending on what the problem is asking for. So here is a sheet that was in our folder for chemistry the week of September 6th. And I'm going to go through the answer key, but there is also a blank sheet there so that if you wanted to do the practice problems and then go ahead and check them to see if you could set them up like I can, going through and going back to the week of September 6th is probably a good idea, right? Anyway, in this problem, it says you find a fossil with 10 grams of carbon 14. According to its predicted weight, the organism had 160 grams of carbon 14 when it died. How old is the fossil? And then they tell you that the half-life of carbon 14 is almost 5,800 years. When you see problems like this, you will normally either see two amounts that are normally in grams, or you will see two times, and it could be minutes, hours, days, years, million, billion years, something like that. But in this case, you have two amounts. You have 10 grams and you have 160 grams. When you have amounts, you need to know what the current or the now amount is, as well as what the kind of then or original or when it died amount. All right. The now amount or the current amount is always going to be less than the amount that it actually started with, because in the decay process, you always start with a large amount and then it is decaying into a much smaller amount. So when you go to set these problems up, you need to know what percent of the parent or what percent of the unstable isotope is still remaining. So that's the very first thing you want to find. And the way that you find that is that you are taking the now or the current amount divided by the original or the then amount. The number on the top should always be smaller than the number on the bottom when you are working with amounts. Once you do that, 10 divided by 160 gives you 0.0625. This is a decimal. The next thing you need to do is to convert it into a percent by multiplying by 100 or moving the decimal two places to the right. Either way, here you get 6.25%. Once you have a percent, then you need the half-life curve to be able to take this percent and convert it into a half-life. So if we go to our half-life curve, all right, and we scroll down here, we can see that on the x-axis, we have the number of half-lives, and then on the y-axis, we have the percentage of parent isotope that is remaining. So that is the percent of the unstable or the decaying isotope. That is the one you need to pay attention to. If they give you something in the daughter is stable, and so it's never decaying, it's already stable, so you always need to find the parent. So in this case, we have 6.25%. So if we go up here, we have 2%, 4%, 6%. 0.25 is going to be a little bit above this line. So we go all the way over to where it actually hits on the blue line, and then go down to the x-axis, which would tell us that if we have 6.25% parent remaining, it has been through 4 half-lives, which is what we've recorded here. Now, in order to find out how old the fossil is, which is what the problem is asking us to do in the first place, we take the number of half-lives it's been through times the amount of time for each half-life, which for carbon-14 is 5,770 years. When we multiply that together, we get 23,080 years. Right? Again, with problem number 2, we're testing a different isotope, hydrogen-3. All right, the half-life is different. Every half-life is going to be different. This half-life is 12.35 years. It tells us that our original or then sample had 250 grams, and our current sample has 31.25 grams. And again, it wants to know how old the sample is. So our current sample, 31.25 grams. Our now sample, all right, so this is, I guess, our now sample, okay, or our current sample, and this is our then sample, which is 250, or our original. If we divide these two, you can again see small number on top, large number on bottom, divide, we get 0.125. If we multiply that by 100 to change it from a decimal to a percent, we get 12.5%. Again, back to our half-life curve. This time it tells us that we have 12.5%. We're going from 10, 12, right kind of almost in the middle here, and we hit the blue line, and it tells us that we've been through 3 half-lives if we have 12.5% of the parent remaining. So then we take the 3 half-lives that has occurred during the decay. Each half-life is 12.35 years. This sample is a little over 37 years, so 37.05 years old. Right, our third problem, and the last one of this type that I'm going to do, says that you're currently testing potassium 40. It has one of the longest half-lives that we kind of know about. All right, so it's 1.3 billion years. And it tells us that our rock currently has 5 grams of potassium 40 in it. Our starting sample, or our original, had 20 grams. It wants to know how old the rock is. Okay. So here, our rock currently has 5 grams, smaller number. We're going to divide it by its original amount, which was 20 grams. So if we take 5 and we divide it by 20, we get 0.25, or 25%. 25% is the amount of parent that we have remaining. So we're going to go back to our half-life curve. Here's 20. We're going to go 22, 24, and go in between 24 and 26, over to that blue dot and down, which would tell us that if we have 25% remaining, we have been through 2 half-lives. And then each half-life is 1.3 billion years. So if we take 2 times 1.3 billion years, we get 2.6 billion years. Right? And then number 4, the answer is there for you. And you could actually try to check that one as well. If you want to try those problems, that would be great. I'm going to go through the other type of problem in our next video. Thanks so much for stopping by.